don't know why PowerPoint won't let me record on there, so I'm gonna have to do it like this. This is my presentation on the synthesis and electrochemical performance of P2 layer material. I did this in Virginia for one of my internships. So for my introduction, right now we depend a lot on fossil fuels for energy, burning fossil fuels, which is not good for our air, which pollutes our air. So sodium ion batteries is kind of like an alternative, because lithium ion batteries, it's not as abundant and it'll kind of move us away from depending on fossil fuels. As I said before, why is sodium ion batteries so important? As you see in the graph, lithium is all the way down here at 17, while sodium is 23,000, which is talking about how abundant it is in the Earth's crust. And when producing the sodium ion battery, in replacing sodium with lithium, you're taking the cost down from almost 1,100 down to 900. And when doing the process of actually making the battery, you cut out the cost of the copper foil because sodium can't lay on a copper foil. Now, the working mechanism of a sodium ion battery. In your battery, you have three components: your cathode, your anode, and your electrolyte. In the working mechanism of the battery, during the charging process, your sodium ions are extracted from your cathode and inserted into your anode. Same thing with the discharging. Your sodium ions are then extracted from your anode and inserted back into your cathode. Now, I'm working with P2 layer material, which is the prismatic structure, crystal structure of the material. So you have your transition metal layer and you have your sodium layer, and it goes AB, AB. And your atoms, your sodium ions, and your transition metal ions are connected by 6 oxygen atoms. For our experimental process, we start off with our transition metal oxide, and we do a co-precipitation where we precipitate the transition metal combination with your manganese, your titanium, and your iron, and 2 different mixtures. And with that, we get our transition metal oxide. We add sodium carbonate and we calcine these at high temperature to then get us a powder that we slurry cast onto a foil to then dry. Then we punch in our electrodes. And then we let those dry overnight. Then we do our coin assembly, which has the top and the bottom. You have your spring, your electrolyte, your cathode, your anode, and we kind of do this in a glove compartment where we smash it all together, because your electrolyte, it can't really be in open air. It's very sensitive to the moisture in the air. So is the lithium and the sodium. Then we take it to a battery cycling machine, which charges and discharges the batteries over time. This slide just breaks down the actual action of co-precipitation. And in this process, the particles are dried. This also explains our calcination process. And in my experimental design, I'm looking at temperature optimization and the effect on morphology of the product, the electrical chemical performance, and phase purity, and also rate capability. So as you can see, this is our original morphology in the precursor, and as low as 700 degrees. So all of these temperatures are all the temperatures we did during the calcination process. This is where we dry the product and get it down to a powder to then slurry cast to make our electrodes. But this is all the temperatures that we did for the calcination. As low as 700 degrees, it's able to retain that original morphology, but as you start to get higher in the temperature, it loses that morphology and it becomes rod shape. It degrades over time. This is our phase purity, where we see this first line indicates that it's phase 2, and as you get up to 1,000, it's no longer phase 2. Not phase 2, P2 material. This is our rate capability, our electrical chemical performance. So this is our discharging. No, this is our this is our discharging, and this is our charging. And as you can see, it really doesn't affect the electrical chemical performance. It actually gets higher over temperature. This is our rate capability, and this is looking at how well it can do with the charging and discharging, and the best performance was at 800. So in summary, temperature does affect the morphology. So as you go up in temperature, the morphology gets worse and it no longer works as the battery. It doesn't affect the electrical chemical performance as I thought it would have, but it does affect the phase purity, whether it'll stay P2 layered material, and it does affect the rate capability, but not really. The best performance overall in all the tests was 800 degrees. So seeing that 800 degrees was the best performance in all tests, for future projects, I would like to see how, looking at sodium content, how much sodium we put into the material will affect all of these things as I mentioned before: temperature, rate capability, electrochemical performance, and morphology. Thank you so much for listening.